why do we need to estimate how many slots will be available? Well, the characteristics of the pure parallel slots in a given cycle depend on the prime visits in that cycle, which you don't know when you're writing a proposal that hasn't been decided yet. But the prime visits in previous cycles are a good predictor of what will be possible in the prime visits for the next cycle. Not perfect, but it's the best you can do. Pure parallel proposals need prime visits with certain characteristics. The main ones are you want to use an instrument, a particular instrument for your pure parallel. So, primes that are using that instrument are not useful to you. So you need to ignore those. How often is that instrument, the instrument you want to use for your pure parallel, how often is that used? Prime visits use, so these are the characteristics of the prime visits that you need for your parallel. Don't use the instrument you want for your pure parallel. The prime visit will need a certain number of configurations. If you want 3 configurations with your pure parallel instrument, then you need prime visits that allow 3 configurations. Prime visits, if you need a certain number of dither positions for your pure parallel, you need primes that have at least that many dither positions. And if you need an exposure of some duration in order to get the signal to noise you need, then the prime has to have exposures that long. So those are the main constraints. Assessing those constraints requires the information about those, what happened in previous cycles, and it requires some software. I mean, a table just won't cut it. So that's what this JWST Pure Parallel package, or JWPure package, will help do. You have to do a little bit of Python, but not a lot. So as long as you have a little bit of Python knowledge, you'll be good. There is a link here to the repository, and that URL is almost short enough that you could type it or Google it. If you wanted to follow along, most of what I'm gonna show now is in the documentation for the tool, which is in the wiki pages that are associated with the repository. So if you go to the software repository at that link and click in wiki at the top of the page, you will get to documentation, and you can navigate over here to see various things I'm going to show you. So you can play along. If you would like to work along here, which I think would be great, you will need to install the JWPure software package. I'm going to talk through this a little slowly so people who want to do that can do it. It's just either the blue box or the green box, or if you have some other way you like to make environments, you can improvise. The first option is to use the built-in VENV virtual environment capability of Python. You will need Python 3.11 or later for this to work, because the JWPure package asserts that Python must be at least 3.11. So you would switch to some directory where you want to do your work, calling it prop in the idea that it might be working on a proposal. And then you would type at the prompt, you would type python -m venv, and then you would give a directory where you want the virtual environment information and the software to be stored. In this case, I'm just imagining it's a subdirectory. You actually don't need the // but I put it there just so you're clear that JWPure is appearing in different places here. That's a path. You can put it wherever you want, though. And then once you've done that, then you can just source in that directory, which now has a bin and an activate. You can just execute this source command, and it will put you in this virtual environment, and you'll have JWPure in parentheses before your prompt indicating that you're in that environment. And then you pip install JWPure from Python package PyPy. Similarly, conda, if you have it, which you might because the pipeline uses it, you would again go to whatever directory you want to work in, although this time the software will be stored off in conda land. But still, you want to go someplace where you want to work. And you would create the JWPure environment using this command, specifying Python 3.11 or later. The -n means, the name of the environment is going to be JWPure, and the -y means answer yes to any questions that are asked. And then you activate that environment, the analog of what's on the other side, and then you pip install JWPure just as you did before. So they're very analogous, and of course the point of using a virtual environment, an environment of some sort, is all the software you run is not mutually compatible. So you want individual environments for different use cases. Create this file. In this case, we're calling it jwpure_test.py in the directory you're working in. And then just say Python and the name of that file, and it should generate this output, which we will go through later, but I'll give you a preview that you get separate results for each cycle, because each cycle is like a separate instance of what might happen in cycle 5. So you get some idea of what the variation is from cycle to cycle in the number of opportunities you would have for your program. And then the pure subset column 0 are slots that were available in that cycle, but were not allocated. Were not useful for the scenario that we described. And when pure subset is 1, that means those are slots that were available, and they have a certain number of configurations and visits and total hours associated with them. All right, so let's go through this. Before I show you how to use that, I want to go back and talk about the data file, which is generally useful. The software uses the data file in a particular way that's supposed to be helpful for a lot of use cases. But if you want, you can adapt the software or just take the data file and use it however you want. And so I want to, and what's in the data file is underlies how you specify your scenario, your pure parallel observing scenario that you want to propose for. So we're just going to go through this. If you want to find the file, there's links to it from the documentation in the repository. But if you've installed it, you can just import from the analyze module this variable that is where the data file lives, and print it out. And I put ... for all of the stuff that's specific to me when I ran this. You'll have different things there. But inside the installation of JWPure, there'll be this file, and you can just use that same path to see that there are almost 80,000 slots that are in that file. And you can look at this CSV file here. I'm just printing to the terminal the first 2 rows. There's these CSV column headers, and then data for the first slot in the file. And we're going to go through what all of these are in a moment. But this is the raw data that we're going to use from previous cycles to assess what's possible and not, what's likely to be possible or not in cycle 5. So we're going to run through these columns that are in there. There's the cycle that the slot was in, the prime visit ID, the configuration that was used, a configuration ID for the prime, and this is something that I made up. You won't find it anywhere else, but it will help us with tracking. It's been difficult in past cycles to know when the prime was changing configuration. So this data file now has an identifier that indicates which slots go with a single prime configuration. And then there's, let me just say, there's a slot ID, which is what we saw in the APT, once you had an approved program, there were all these slot IDs that were assigned to you, and you could connect your pure parallel observations with those slot IDs. Those slot IDs don't actually indicate when the configuration changes in the prime, which is why I said that was an issue. So this file also has an alternate slot ID, which just basically has the config ID plus a counter that increments for dithers usually, although it could be multiple exposures without dithering. Whereas the slot ID that currently is in APT just counts sequentially through the whole visit without resetting each time the prime configuration changes. So that'll help for people that are trying to figure out how many configurations they can do in the pure parallel without having to go look at the APT file for the prime. And then there's the slot duration, which is how long your pure parallel exposure can be. All right, then there's the pointing information. There's the RA and deck of the prime will be in an adjacent field. There's also the equivalent ecliptic latitude, which would be useful if you're trying to do a solar system survey of some sort, and galactic latitude if you're trying to do some galactic science. There's an orientation field there if the prime specified an orientation for some important science reason. It'll be recorded here. In principle, you could use that information to figure out, calculate where the pure parallel field will be. The software package that I'm describing does not do that, but the information is here. There's the category of the prime program, which isn't really useful, but it's there just for information. There's the prime instrument, which is very important because if you want to use MIRI for your pure parallel, then you can't be attaching to primes that use MIRI. There's the observing mode, which in principle isn't important, but I was thinking that in some cases you might eventually figure out that the dither patterns that are used with the IFU are not big enough for your purposes, or the NIRCam ones are too large for your purpose, or whatever. So in certain specialized cases, it might be useful. You could also calculate the dithers yourself from the RA and deck of the prime, but that would obviously be a lot of work. And then there's the data excess for the visit. These are slots, so every slot in the visit will have this exact same number, which is the data excess for the visit. It's not really useful or interesting to calculate data excess exposure by exposure, but I wanted it to be handy, so it's there. And then APT specifies some indexes under the hood that say which target in a target group are you looking at, which tile in a mosaic are you looking at, which configuration within a target and a tile are you looking at, and which pointing dither offset are you looking at within a config. So normally APT nests things just the way it's listed here. For the IFUs, it's reversed. I mean, it's slightly different, but it doesn't matter. These are the indexes that I am making available here in this input file, and these are what are used to generate the configuration IDs that I showed up here. So there's these extra numbers that were sort of magical here, and I said the T is the APT target, the TT is the tile, CC is the config. Those are just listed explicitly here as well, just to see where things are coming from. It does help to sort of understand what's happening in a visit if you can see the indexes here. So, all right, so that's the input file. Now let's talk about how to use it. We're going to step through this example in detail, which is in the documentation under the Analyze a Scenario tab. So first we import the scenario class and instantiate it into a lowercase scenario object. This reads that data file that I just talked about, and it loads it into a SQLite database in memory, just to allow more efficient access. Each time you can have multiple scenarios going at once. Each instantiated scenario is independent, so you can compare them if you want. Next, we need to, I can't highlight it. So next, the top line here, we need to get in our local namespace three objects, three variables: slot, config, and visit. We get them by, you can use the lowercase scenario, but these are the same no matter what. So you can use the uppercase scenario. These are class variables. And if you print each of those, it'll list what the attributes or properties are of each of those. And these correspond to some of the columns, but not all of the columns in the input file. So what is the prime instrument? What is the duration of the parallel slot, the array, the deck, the ecliptic and galactic latitude, the number of slots, total slot duration, the sum of all the slots, and the number of configurations. And the reason they're each in three different bundles or containers is that the number of slots is not a property of an individual slot. It's a property of the configuration. And the number of configurations is not a property of a slot or a configuration, it's a property of a visit. And it's necessary to make that distinction and to make the magic that you'll see in a moment work. All right, so slots are properties at the exposure level, as I just said. Slot duration is the maximum duration that a pure parallel exposure can have, given the duration of the prime exposure. It's the same for all slots in a configuration, because that dither pattern, if you remember back to the visit file, there was just one exposure specification for all the dithers in the prime, so the duration is going to be the same, except that the first slot for NIRCam is a little bit longer, and the first slot for MIRI is also a little bit longer. So later, when you see how to constrain the slot duration for your pure parallel observation, you need to keep that in mind, that you may, if you're saying, I don't want it to be longer than some duration, you might be chopping off the first one accidentally. Configurations are properties at the prime instrument configuration level. Each prime configuration corresponds to one of those activity statements in the visit file that I showed you earlier. And as I have been saying repeatedly, the parallel instrument can only have one configuration per prime configuration. There's also a convenience variable defined, which is not in the original input file. It's the total duration of science time in a configuration. And that's there so that if you're searching for opportunities to get a certain total amount of exposure time in a given configuration, and you don't really care whether it's 3 500-second exposures or 6 250-second exposures, you can use this config duration, the total duration of pure parallel exposure time in a given configuration in your constraint. I'm going to describe how to do the constraint momentarily. And finally, visits have a number of configurations. And just a warning here that not all configurations, so all slots in a configuration have similar properties modulo that extra little bit of time I just discussed, but the configurations in a visit can be quite different. You can have a target acquisition followed by a longer science exposure. You can have different exposure depths for different NIRCam imaging filters. You can have a direct image and the dispersed images. So just be aware that the number of configurations is a property you can look at, but you have to be careful that the exposure duration is different. The properties of each configuration could be different. All right, so now finally at last we're going to specify a constraint. And again, this is like, I want to do pure parallel science of some sort. I need some characteristics for the primes. This is where you describe it. And we're just going to use these objects in in Python expressions with normal looking operators and the arguments of interest, and the constraint will magically capture all of that. So in this case, we're saying we don't want the instrument, the prime instrument, to be MIRI, because we want to do MIRI as the pure parallel instrument. And we want to have at least 4 configurations, because in this case, let's say we want to have 4 different filters with MIRI. So that's it. We just specified the constraint. The operators that could go in a constraint, must be equal to, must not be equal to, greater than or equal, less than or equal, is in some list. So like the instrument is in this list or that list. So, I only want primes that are or are not these instruments. Between, so if you want to limit exposure time or galactic, latitude or whatever, you would use this syntax. In this case, it's saying I want the slot. This example, it's the slot duration should be between 300 and 900 seconds. I'll warn you again, if you limit it with a top end, like no longer than 900 seconds, not works, and then and or. You'll notice that there are parentheses in these ands and ors, and in fact, I want you to use parentheses around all your atomic things and higher level constructs when there's an order that's important, so that you're absolutely 100% confident that the constraints are being evaluated in the order that you intend, and not whatever would be specified by operator precedence in this kind of bizarre Python operator space. All right. Now we've got a constraint. We've instantiated a scenario, and we've got our constraint variables, and we used it to specify a constraint. Now we're going to allocate slots out of the pool of slots that were in that input file. So here's the algorithm. First, we find all slots that satisfy the constraints that we just constructed, ignoring all slot level constraints, ignoring for the moment the config and the visit level constraints. So initially, the first time you do this in a scenario, the first time you allocate slots in a scenario, all of the slots are available. And at the end of the first call to allocate slots, and then in subsequent calls, only a subset of the slots will be available, because we will have allocated some of them in the first or previous times we called allocate slots. So you can, the use case for this, just to have something in your head, is I would really love to have 4 configurations for my pure parallel program. So how many of those can I have with at least 4 configurations? And then, having used all of those slots from the pool, I can still do useful science with 3 configurations. So how many of those could I get? So that's the reason why, an example of why you might want to call allocate slots multiple times, and why there's this logic of first they're all available, and then later only a subset is available. Then distill the slots identified in step 1 to a list of configurations that contain those slots. And then for each of those configurations, calculate the total number of slots and the total config duration. And then pare down the list to be only those slots that satisfy the config level constraints. How many configs did you want? What was the total duration? Then you distill those configurations down to a list of visits that contain those configurations. And finally, you calculate the visit level constraint, number of configs. I said a moment ago number of configs, but it was really number of dithers. Anyway, finally, you've applied all of the, you're not doing all this. This is happening under the hood in allocate slots. Allocate slots sets this variable, this parameter, which is in the output files we saw, pure subset, to 1 for the first call to allocate slots, 2 to the second, etc. So you'll have information, summary information and detailed lists of slots, and you'll know which pass through the allocation process each one of those slots was allocated. All right, so then finally we go to the output. I think we're near the end here. So you can get a summary by just saying scenario.summary, and it'll write this little table here. As I said earlier, this pure subset is 0 for all the slots that were not allocated, 1 for the slots that were allocated the first time you called allocate slots, which in this example we only called it once. But if we had called it a second time, there would, for each cycle, there would be another row that had a 2 in the pure subset column, and the number of slots, configurations, visits, and hours that go along with that second allocation process. And then also there's a where statement at the bottom, which documents in SQL speak what your constraint looked like when the query was made against the SQLite database that's living in memory. You can also write that exact same information to a text file by just specifying path equals and then the name of a file when you call summarize. And as the green box says, again, pure subset just tells you unallocated or which allocation. And this just describes what's in that table. Just to say, number of slots is the total number of pure parallel slots that you allocated, the number of configurations that you were able to allocate, the number of distinct prime visits that you attach to, if you will, and the number of exposure hours that are available that were in that allocation process. All right, you can also use the save method in scenario, which will write a CSV file, which you must specify. The first 19 columns are identical to what was in the input file. And then there are 4 new columns, which has the pure subset that we've been talking about to help you know whether it was well, these are all allocated. So this only writes the allocated. So there's no 0 anymore in pure subset in this output file. There's only 1 and then 2 or 3 if you do multiple allocations. And then pure visit is a running index, the first visit that you use, the second visit, and so forth, just to help you distinguish, okay, now I'm in a new visit, now I'm in another new visit. And similarly for config ID and for slot. So it's a nested thing with these indexes. It's a lot easier to see what's going on than if those indexes were not there.